So I'm a little bit embarrassed because I'm basically a mathematician, so I never studied until recently linguistics or mathematics related to linguistics in any depth. So I'll probably say a lot of naive or stupid things. Okay, so I want to say a couple of words very speculatively as some motivation introduction. So the best known
Sergey, sorry, the voice quality is very bad. I think when you move, maybe you're bumping into your microphone or something. So when you sit still, it sounds good, but when you move around, it starts really.
Okay. I will be fixed. Is it okay now?
Yeah, now it's perfect.
Okay. So best known categorial grammars, logical grammars are, so to say, non-commutative, like lambic grammars. So they use non-commutative logic or non-symmetric monoidal categories. And there is a more recent approach using commutative systems like abstract categorial grammars, ACG, which are based on the ordinary intuitionistic linear logic and linear lambda calculus. And so they have their advantages and disadvantages. And on the positive side, of course, the underlying logic is much more natural and intuitive, and they are great. They are very expressive. They go far beyond context-free languages and maybe even too expressive. And in some situations, they are remarkably flexible, not always. And in a striking difference, at least for me, from more traditional approaches, the basic entities, basic language elements, so to say, in these grammars are extremely abstract. They're just linear lambda terms. And it's not easy to think of a concrete piece of language as a lambda term. So apparently it would be good to have a more concrete surface representation for these systems. And well, there exists a very concrete and natural category, symmetric, compact category that I will be discussing, where these grammars can be interpreted. That is one thing. And concerning distributional compositional models like DiscoCat. So DiscoCat uses a symmetric compact category, this kind of structure, in a very essential way on the semantic side, like vector spaces or other models of meaning. But on the syntactic side, on the language side, we usually have non-commutative systems like lambic grammars, pre-group grammars. So I think it might be interesting to have on the syntactic side also a similar structure, symmetric monoidal, symmetric compact category. So I'm saying that it would be interesting. I'm not saying that it is necessary or even that it would necessarily be useful. But I think it would be interesting, and anyway, such a structure exists. And well, I think that if some mathematical structure exists in a more or less natural way, it's usually for something. So that was motivation. Okay, so the first entity in this category, the objects, I call them boundaries, and the boundary x is defined by a natural number, the cardinality of x, and an integer interval, a subset in the integer interval from 1 to the cardinality of x, which I call the left boundary and denote as x sub L. There's also the right boundary, which is the complement of the left boundary. And so elements of the left boundary are left endpoints, and the elements of the right boundary are right endpoints, and they have left and right polarity respectively. And here is how I depict these boundaries. So a boundary is essentially a finite totally ordered set, which is subdivided into two parts, into the left and the right sub-boundaries. And so here is a boundary with 5 points, and 2 of them are left endpoints, and I denote them as solid, thick dots. And information about the boundaries in the picture. And there are operations on boundaries. So there's tensor product, which is just a disjoint union, or it can be, in some sense, it's a concatenation of boundaries. We take two boundaries and just put them together one after the other. And there is duality, which I denote as perp, which reverses the order and polarity as in the picture. So here we have two dual boundaries. We can see that there's a bijection between their points, which flips polarity and reverses the order. By the way, this duality flips tensor factors, and this should not suggest any non-commutativity. In fact, duality will commute with tensor up to a natural isomorphism. Yes, and there's the unit, the tensor unit, which is, of course, the empty boundary. And the next entity I call multi-words. So I first define a regular multi-word. Regular multi-word with boundary X over an alphabet T is a directed graph whose vertices are enumerated as points of the boundary X, and the polarity is respected so that every edge starts at the left endpoint and ends at the right endpoint. And also every vertex is adjacent to exactly one edge, so it is a perfect matching. And edges are labeled with words in the alphabet C. Here's an example. Here is a boundary. Here is a multi-word with this boundary. There might be some ambiguity about how to read these pictures, how to read edge labels. So my convention is that I read the word labeling an edge in a normal way from left to right, because the edges in the picture can go in any direction, but whatever is the direction of an edge, the word is read from left to right. So this edge is labeled with XY, this one with BA, and the last one is labeled with the empty word. And unfortunately, for consistency of definitions, we'll have to consider somewhat pathological multi-words which are not regular. So general multi-word is defined as a pair. A regular multi-word, the regular part, and the singular part, which is a finite multi-set of cyclic words. A cyclic word here means a cyclically ordered sequence of letters. Here's an example. So this is a general multi-word. This is the regular part. And there's a singular part which consists of two cyclic words. I depict them as isolated loops. And I repeat that these are not words. They are defined up to a cyclic permutation. So I can write this cyclic part, singular part, I can write it differently. A basic operation with these multi-words is gluing. So in a multi-word, we can glue edges along points of opposite polarity. So this is underspecified what I said, because it's more or less clear how to glue edges in a graph, but we also need to glue labels. So the prescription is in the pictures. Like in the first picture, we glue two edges along these intermediate points. So we obtain a new edge. We look at its starting point, which is I. Then we read the label, which was adjacent to the starting point. We read it first, and then we read the second word, and we concatenate them in this order. So the label of the new edge is ZTXY. And in the second picture, the order is different. When we glue these two edges, what we get a new edge which starts at J, So in order to read its label, we go first to J, we read the label which starts at J, and then we read ZT and concatenate the words in this order. So it's X, Y, Z, T. So we always read the label of a new edge starting from the starting point of this edge. And there are also pathological cases when we try to glue an edge with itself, as in this third picture. In this case, the edge and its label become a cyclic word and go to the singular part. That is how singular parts arise. A crucial thing about these gluings is that we can do a lot of such gluings in a row, and the order doesn't matter. So we can do them all at once. I give an example how this works. So this is a concrete long multi-word labeled with words of natural language, and we do 3 gluings. So this picture is actually taken from a concrete derivation. So obviously, if we ignore labels, we will obtain just a single edge after these gluings. And so the question is how to read its label. Well, we read it according to the prescription starting from the start. So it goes Jim, and then we jump loves, and then N, and then medley. So Jim loves N medley. That is how it works. And now I'm ready to introduce the main entity, the morphisms, which I call word cobordisms. And I think it's okay to abbreviate this term as cobordism. So if we have 2 boundaries, X and Y, then a cobordism from X to Y is a multi-word with boundary Y tensor X perp. And here's a concrete example. We have 2 boundaries, and here is a multi-word representing a cobordism from X to Y. Now, the boundary of this cobordism has 2 parts. One of them is parameterized as Y, and it corresponds to the output. So it's the outgoing boundary. And the other one is parameterized as X perp, but it corresponds to X. It corresponds to the input. It is the incoming boundary. And my convention for depicting cobordism as a cobordism, not as a general multi-word, is that I put the outgoing boundary on one vertical line, the incoming boundary on another vertical line, and note that I order the points of the outgoing boundary from the bottom to the top. And as for the incoming boundary, so it is parameterized as X perp, and as points of X perp, these points are ordered in the picture from the top to the bottom, but morally they correspond to X, and from the point of view of X, they are also ordered from the bottom to the top, because X and X perp have opposite order. And so this is a strict convention, and these numbers are redundant. All information is in the picture. And of course, usually we don't know the exact structure of a cobordism, so I depict just a box with incoming and outgoing edges. And more often we don't know the structure of boundaries either. So a more schematic squeeze picture is just a box with an incoming and an outgoing wire, which is familiar. And so if we want to emphasize that these boundaries are compound, that these are tensor products, I depict multiple wires. Note that I order the tensor factors in the picture from the bottom to the top, as my convention requires. And well, yes, so every wire here represents in a quite direct way a parallel cluster of edges. And so this guy composed, so I give a schematic picture, but I think it's clear. They're composed by gluing along the outgoing boundary to the incoming boundary. So it's a multiple gluing, as as has been discussed. And so this is an associative composition, and if we fix an alphabet T, we get a category, which I denote coord sub T, which has a lot of structure shown in these pictures. So there are identities and tensor product, which is a disjoint union, and there are symmetries. So this is a symmetric monoidal category, and duality, which is a contravariant functor defined on boundaries and morphisms. And this is, of course, just a common graphical representation of a compact category. But I want to stress that in this case, this schematic picture represents actual coordinates very literally. So if you want to go from a squeeze picture to a more detailed picture, we just need to substitute for each wire a parallel cluster of corresponding edges. And then if we know what is inside the boxes, we recover the actual coordinate. This is thanks to the definition of duality as a reverse in the order. Okay, so a lot more pictures can be made. So there are caps and cups and names and conames. And in short, this is a compact category. So we can move objects between inputs and outputs. And in a sense which can be made precise, this is in fact a compact, a free, it is not seen in the slide. It is a free compact category generated by a free monoid, where monoid is considered as a category with a single object. And as any compact category, it is a model, a degenerate model of multiplicative linear logic, of multiplicative intuitionistic linear logic, and of linear lambda calculus. And this allows interpreting logic grammars or defining logic grammars. So here's a picture how linear lambda type to linear lambda calculus is interpreted. So we need to assign to each atomic type a boundary. Then this interpretation extends to all types by this formula, and derivable typing judgments are interpreted as coordinates of corresponding boundaries. And here are two pictures for two rules of linear lambda calculus. And a careful inspection of these pictures will show that this is invariant under beta-eta equivalence. And speaking about logic grammars, so string abstract categorial grammars, string ACG, they translate with all derivations faithfully into this language. So this is indeed a surface representation. But I think that for this particular category, for this particular denotational semantics, a more natural logical system is classical multiplicative linear logic, which also can be interpreted in this setting. I will not go into details. I will not probably remind the syntax of linear logic, but it's in the slide. Interpretation consists again in assigning a boundary to each positive literal, and then this extends to all formulas or types in an obvious way. So I note that par of linear logic is interpreted here, will be interpreted as tensor with fleet factors. Yes, and the sequence will be interpreted as a big par, so it will be a tensor of its formulas in the opposite order. And proofs will be interpreted as cobordisms. Again, I don't go into details, but here's a picture for the rules. I comment here that pictures are rotated 19 degrees counterclockwise, so that the boundaries are on horizontal lines. And the points of the outgoing boundary are ordered from right to left. So this is convenient because then the order of wires in a picture is the same as the order of formulas in a sequence. Okay, so this interpretation of of multiplicative linear logic, and if you want to define a kind of logic grammars, so we add a set of non-logical axioms, so to say. So what can be a non-logical axiom in this setting? So non-logical axiom, it's a pair consisting of a sequent, which is properly a non-logical axiom, and a cobordism to the corresponding boundary, which represents its sort of its proof in quotation mark. So I call this pair a cobordism type in judgment, and I read it as sigma is of type gamma. And then if we fix some cobordism type in judgments as axioms, we can we can generate more and more cobordism type in judgments using rules of linear logic and their interpretation in the category of cobordisms. So I call this structure and interpretation and the set of axioms a cobordism signature. And the grammar, linear logic grammar, LLG, or maybe a cobordism grammar or a tensor grammar. So I'm not sure about a good term. So it's a cobordism signature where everything is finite. So there are finitely many positive literals. There's a finite alphabet. There are finitely many axioms. And also there is a distinguished sentence type S, which is a positive literal, such that the corresponding boundary has exactly one left and one right endpoint. So what does it give us, this sentence type? Any regular cobordism, which we can derive from axioms, any regular cobordism of type S will consist of a single edge, which will be labeled by some word. So the set of regular cobordisms of type S can be identified with a set of words, which is a language generated by grammar of this sort. So there are some formal expressivity results. So concerning abstract categorial grammars, string and tree ACG embed into these LLG as conservative fragments, essentially because in Chinese linear logic and linear lambda calculus embed into classical linear logic as conservative fragments. So it's an open question whether in terms of generated language, these LLG are strictly equivalent to string ACG, or maybe they're a little bit more expressive, but I think that they're equivalent. Another nice expressivity result is that a language is multiple context free if and only if it is generated by an LLG with a tensor free lexicon. This, by the way, implies that the known result, that second order string ACG, are multiple context free. And on the less positive side, like other commutative categorial grammars, these LLG are maybe too expressive, so we don't know even if they're decidable. And we know that the general LLG, just as an ACG, can generate an NP complete language. Actually, I have a last slide where it is shown how to do it, but it's actually quite easy and instructive, but maybe it's too much, so I'll skip the last slide. Yeah, so it shows how to generate an NP complete language. Well, if anybody is interested, you can ask me. I think it's enough. So that's it. So here are references for a detailed paper and some other stuff. Well, thank you.